Hello everyone, thank you for watching this presentation. The title of the paper that I'm going to present is an axiomatic approach to detect information leaks in concurrent programs. My name is Sandip Ghosal. I'm a research scholar from Department of Computer Science and Engineering, IIT Bombay, India. This is a joint work with Professor R.K. Shyamasundar. In this presentation, we'll introduce the notion of leaky assertions for concurrent programs that exhibit program points using various public statements, for example, print, sleep, delay, etc. Next, we describe how these leaky assertions can be used in standard program specification and placing the leaky assertions at appropriate observable program points would help us to capture the information leak through these public statements. How information is leaked through public statements? So let us understand one incident of information leak using this example. Let us understand this thread T1 and T2, where age is a secret variable. So a public observer would try to understand the value of age. Await is a standard mechanism for process synchronization through a shared variable same. And there are four public statements: print A, print B, print C, print D. Let us take one incident of execution where thread T2 is executed in between print A and print B. Now, the output sequence A, C, D, B would help the public observer to understand the value of age is 0. So, if age is 1, then it would enter into this if block and it would wait T1 to complete. Now, if age equals to 0, then it will not enter into this if block and go on to print this D. Therefore, the sequence A, C, D, B would help the public observer to understand the value of age is 0. Now, to capture this information leak, we have used the force triple specification for partial correctness and the notion of functional correctness as defined by Osicki and Gris. Let us understand, let's say that P and Q are precondition and postcondition for a statement S. Then force triple says, if P is true before execution of program S, then Q holds if and when execution of S terminates. This is written as PSQ. Then given a proof PSQ, a statement T is non-interfering if the concurrent execution of S and T will not invalidate the pre and post condition P and Q. So in this case, a key idea is that we derive the leaky assertions and try to establish these functional correctness for a statement, and if the leaky assertions are not invalidated by the functional correctness, then we say the statement is leaky. Let us understand from this example. For deriving the leaky assertion, we have borrowed the notion of auxiliary time variable from the work of Lamport in establishing correctness of real-time programs. So we have taken a variable t and initialized with t, capital T, at L0, and also we have initialized the time variable t with t prime at the public statement print D. Now, the execution time difference between these two statements would help the observer to understand the value of H. Considering those leaky assertions as precondition for the statement print D, if we try to establish the functional correctness for functional correctness properties, then we can see that if those leaky assertions are not invalidated by the properties, then we can say the program is leaky. In future, we'll try to automate this whole process, and towards that goal, we have developed a dynamic leveling algorithm to identify the leaky public statements. Dynamic leveling algorithm works in combination of static and dynamic leveling, where we try to bind the level of global variables statically and the local variables dynamically. So dynamic leveling algorithm would try to provide the final level for each of the local variable for a given set of static global variables, global levels. Now, if I consider a public statement as a global variable and we label it as low because it is visible by the public, and whenever a higher variable would try to be printed on that standard output, then the dynamic leveling algorithm would indicate that there might be a possible violation of information flow properties. In that case, we can identify this is a information leak. Now, next we will try to capture the time sensitivity for deriving leaky assertions corresponding to leaky public statements using various program analysis tools and oracles. And we'll try to arrive at a possible interactions of concurrent programs, and finally apply model checkers to check for certain properties in presence of given assertions in other components. So that's all. Thank you for watching this presentation. If you have any questions, please mail me in the email given in the paper, and also you can participate in the chat in the open session. Thank you. Thank you.
Good afternoon, everyone in Europe. We are with the author of the paper, and it is time to make questions and get the answer. Right now, we have a question. Deep, when you wish, you can go ahead and start.
So the question is, what evaluation experiments or proofs have been done for this work? So for this work is in initial, we haven't got any experimental evaluation for this work, but the proof is in line with the correctness properties of OCK Greece, and as we have the auxiliary variables for deriving the leaky assertions. So uh, with the Lamport's work.
I'm not working in this area, but I know that the proofs, this type of proofs, are quite complicated. Calculating weakest preconditions for simple code structures like if, thens, and the like is pretty easy. But when, for instance, you have loops, then the situation gets quite more complicated.
Right.
Does it have any implication for your work?
So implications in the sense, so I'm not able to understand exactly what you were asking. So if you are asking about the proof assumptions, and so assumptions are also based on the work of the OCK Greece work, and also basically we have borrowed the concept of the non-interference defined by the OCK Greece, and we have used the mechanism or techniques that Lamport has used to prove the correctness for real-time programs. So we have these two, and we have tried to uh, proof system for identifying information leaks in concurrent programs.
Did you plan to? I'm sorry, go ahead.
Yeah, basically the proofs are in line with their work.
I'm curious, do you plan to move from the theoretical computer science, let's say, area and go to more applied fields? That is, once you find that some code is potentially leaking, what to do with it?
Yeah, sure. So basically, in future, I will be interested to apply these and implement a model checker, which will basically validate this. And so, for a given particular concurrent program, it will first identify that where the program could be leaked and what are the potential program point, and then it will try to derive the leaky assertions, and a model checker will try to validate those leaky assertions. So these are the basically steps that I'm trying to follow. Done is we have developed a dynamic labeling algorithm which would basically give the security labels to each program point, and then will try to identify what are the potential program points which could leak information.
But we need to remove those leaking points or those potential leaking points. That is, it's concurrent programming, of course. It's more complicated that sequential, what regular programming. But we need to remove those statements that create the risk. Don't we?
Yeah, sure. So that is feedback to the programmer. So now it's onus of the programmer that to correct the program and to these are the basically the program points which are basically vulnerable to information leak. So this is basically the work.
Perfect. So everyone, it's 20 seconds to finish. You are cordially invited to join the discussion room that is going to show up in your computers with the author Sandip, and you just need to press the button join discussion room to keep on talking about this paper. Thank you very much.
Thank you. Thank you for watching this presentation, and thank you.
My name